I'll get the exam done. All right. I know it's probably kind of long, but hope it went okay. We'll get that graded and back to you. So I was thinking, I think the final exam will be similar to that exam, and I'm likely just going to cover the last part of the class on the final. So we're not going to have like a double long final that we cover everything. I mean, we're kind of like, it's comprehensive already, the material in a sense, right? Like to solve, multi-dimensional, transport problems, you're still going to have to know the equations and where they come from and that kind of stuff. So just sort of a heads up of what I'm thinking there. So we are now going to jump into, yes, we got Roya. Okay. So we're now going to jump into trying to solve problems with more than one independent variable. So up until this point, we've been sort of trying to understand the equations, right? Where they came from, what they say physically, what the simplifications are. And we solved some of the like classic one-dimensional steady state problems. Okay, but we're kind of like out of those. I think we've solved like almost all of them, right? I mean, maybe not all, but like all of the cases of them at least. There's only so much you can do, right? With the second derivative equals 0, different ways you can kind of arrange those and solve it. So we've done that a lot, okay? So to do more than one independent variable, we're going to have to start solving partial differential equations, right? So if you think about the math that we did in the past, it was a lot of times separate and integrate. And occasionally, if we'd have like a linear ordinary differential equation, we couldn't separate and integrate. Rely on our ODE's knowledge or turn to that table in the back of the book, right? Look it up and go, okay, we're good with that. And now we're going to have to do PDEs. And so this class isn't a PDEs class, but it's also, I want it to be a little self-contained, right? So I assume some of you may have had PDEs, some of you hadn't. So we'll talk about their solution and we'll sort of see how in depth we go. I think I'm going to try and take from you a little bit of the cue about how much you know about some of this stuff, okay? And so we'll see how deep into the weeds in the math we go. But also, sort of another point to make is, as the math gets harder, it takes longer to solve any one problem, right? And the solutions start to get rarer and rarer that we can do by hand, right? So as you might imagine, like as you start to throw in a lot of different variables and different geometries, it gets hard to come up with a solution. And so these problems tend to be, I tend to think of them sort of like case studies. Like every problem starts to become a thing on its own, almost a separate subject even, to sort of, okay, how do we solve this problem? There's this way, and this leads to these things. There's not really a lot of, there's one method we learn, and then we can solve 25 problems by that way. Right? Like that gets increasingly rare. So that's just sort of a high-level preview. So one of these things that I think is really important to sort of point out about this is that with these case studies, they kind of become your go-to patterns that you see when you then think about transport. And so we've seen some of these, right? Like Couette flow is this classic case, right? And we kind of have the same, linear concentration profile or linear temperature profile that we get Couette flow. And hopefully, as you see transport, you start to see that that's sort of a foundational building block of transport problems, okay? What we're going to do today, a similarity solution, okay, to a transient diffusion problem. It's going to be the same thing, okay? It's sort of one of the foundational problems. And if you go into different engineering, a lot of times they'll learn this, but they might learn, if you're an electrical engineer, maybe you learn how to solve this with when you're thinking about electric fields or some other physical situation. So this becomes sort of your go-to thing to think about, even when you think about the math, right? You sort of think of the physical things we'll talk about today and how that applies. Okay, so I don't know if I'm just trying to give a little perspective to motivate what we're going to do. But sort of, are there any questions? So that was my initial comment. So is there any question about what I'm saying. Maybe it's sufficiently vague that you don't care. It's early. Just walked in. All right. Okay. So 1, I did. Let's do 2. Problem setup. Okay. So we're going to consider the following physical scenario. So consider the following. Okay, suppose I have a flat plate, okay, and there's fluid above it. All right, and I'm going to give this the x direction and the y direction. Okay, and this is at time equals 0. I've got some flat plates in there with fluid above it. Okay, and then at some time greater than 0, okay, this plate starts moving with velocity v0. Okay, so sometimes we call this an impulsively or suddenly started flat plate. Okay, so just sitting there, all of a sudden we start pulling them. All right. So let's think about what we would expect the velocity profile to look like in this situation. So, you know, if I plot on these axes, I'm going to put Vx on this axis, and I'll put y over here. So what do we expect to happen? What do I think about the velocity at y equals 0? What do you think it's going to look like there?
The time equals 0, the time greater than 0.
Let's think about all time. So time equals 0 doesn't look like anything. Okay. So what happens as soon as I start the plate?
So at y equals 0, the dx should be the velocity should be the v naught.
Okay, right. So I should put v naught there. I'm going to get a velocity that looks like that at the very beginning, right? And then what happens a little bit after that? It's probably going to like start to move the fluid above it, right? So like a little bit after it, I'm going to get something that looks like, you know, maybe not that far. You know, it looks like this, right? You know, so that would be like time, you know, small, right? And then a little bit later, it's going to look like that, right? Because now, as I'm pulling it, I'm going to get more fluid sort of pulling on the parts above it and above it. And so later, I'm going to get something like that, right? And so, you know, this one's like T2, and that one's like T3. Maybe we'll call that one T1. Okay, so it's still going to have no slip at the surface that's going to cause it to be moving the same speed there, but farther and farther away, it's going to speed up. Okay, so, you know, what are some of the principles? There's no slip at y equals 0. There is, so if we think about this, there's only velocity in the Vx direction, right? Because that's only the velocity I'm injecting. I'm never injecting velocity in the y direction. So there's only Vx, okay? And Vx is a function of y and t, right? So it's not a function of x, right? The velocity here is the same as the velocity farther along in the x direction, right? It's only varying in the y direction. But it does change in time, so it's transient. Okay? And we see that it's sort of penetrating deeper and deeper into the fluid. Okay, so let's kind of take this intuition we've developed and let's go to the math for a second. Okay, so where should we start? I'm thinking Navier-Stokes equation, right? So you can always start there. I don't want to go back and do the balance. We've done a lot of those. We can just start here at the Navier-Stokes equation. Rho dv dt equal to minus grad p plus mu grad squared v plus rho q. Okay, so let's think about, we said it's unidirectional, so it's going to be, Vx is a function of y and t. So if we think about that, we're going to only write down the x component, right? So let's write down the x component. So it'll be rho dvx dt plus, let's say it's v dot grad v, so that means it's vx dvx dx plus vy dvx y plus v or vz dvx v. That's that side. And then the x derivative on the pressure minus dp dx plus mu. Then we have grad squared vx only, right? So this should be second derivative of vx x squared plus the second derivative of vx y squared plus the second derivative of vx z squared plus rho gx. Okay, we think I got that right. So now we need to cancel some terms. So let's see, who can tell me, maybe I'll pick on you. All right, Mark Swanevelt, that term, zero or not zero?
Isn't it non-zero?
Non-zero. Okay, so we're going to keep that one. I'll underline the ones we'll keep. We'll cross out the ones that we think are zero. Okay, Brian.
That'll be zero,
Zero. Why?
because Vx is a function of y and t, not x.
Right. So that's zero. Okay. Zach, that term.
I would say 0. So there's when we plot the y, is that a vy that's going up? Because I know dx
Yeah, that's
changes.
Vy, right?
Okay, then I would say non-zero. I'd leave it.
You think it's non-zero?
Wait. Sorry.
Okay, this is a good question. Okay, so let's think about each of these two terms. So there's Vy and dvx dy. So which one?
Vx dy is non-zero.
That's non-zero, so that can't be it. Okay, the question is Vy.
So I know there's vx. That's
Vx.
we're also making a flow that's going in the y direction.
We're not making a flow going the y direction. Vx is penetrating
Oh, okay.
into the fluid above.
Okay.
Right? So up here, it's still, but there's no velocity pushing it up. Right? Like there's nothing flowing up. I've only added this direction. Right? So this is like this is at least for laminar case. So if I pulled really fast and I started creating vortices, then I could get flow that would go up. But let's keep it at the low enough Reynolds number, okay, that I can just assume Vx is this, and then I have Vy.
Okay.
Vz equals 0. Okay. So, okay, let's do that. So that one's 0. Okay, let's come around. Christina, what about that one?
0.
0 for the same reason, right? I got a 0. Okay. Andrew, what do you think?
I think it's not a pressure-driven flow, it's a like shear-driven flow, so I think it's 0.
Yeah, I think that's right. Okay, and think about it. This is saying even more. It's saying dpdx. So is there a pressure change here versus here? Right, this fluid's like connected. There's nothing driving it. So dpdx is 0. Okay, we're at Roya. Let's see this one.
0.
0, right? Because it's not changing that direction. Okay, Mark.
Non-zero.
Non-zero. So that one stays. Okay, and then I guess we're out of people. I guess, oh, we have online. We're not out of people. How about Dan? This one. I don't know if he has a microphone.
He said 0.
0. Okay, and let's see, we have the other Zach on there. Zach. This one. No response.
0.
0. Okay, perfect. 0. Okay, so what are we left with? That was awesome. We got lots of things gone. So we're left with only rho dvx dt is equal to mu second derivative of dx dy squared. Okay, we can simplify that a little bit and combine these, and we get dvx dt is equal to nu d squared dx dy squared. That's all will be right. Okay. So those are the only terms that are left over. Okay, so what does that look like? That's a diffusion equation, right? Transient diffusion equation in one dimension. So that's kind of interesting to think about. We can readily think about an analogous situation in both heat transfer and mass transfer, right? What would it look like for heat transfer? What would it look like for mass transfer? Okay, I want you to take just a minute, pick one, pick either heat transfer or mass transfer, and write the equivalent of this equation for heat transfer or mass transfer. All right, did you come up with one? What do you think, Andrew? Which one did you pick?
I wrote down the one for temperature for heat
For
transfer.
heat transfer. So what'd you get?
D big T dt equals K d squared T over dy squared.
Okay, almost, but there should be a rho CP on here. So this thing becomes alpha,
Okay.
right? So remember that we have this kinematic viscosity is like our momentum diffusivity. And then alpha is our thermal diffusivity. Okay, did anybody do a mass transfer one? Lord?
d dt equals dab d squared c p y squared.
Right, or that, I'm going to put a little A on it just to give us an A or a B, right? So exactly, so now we have the mass diffusivity there, right? Okay, so that's great. So this problem, right, in the right circumstances is, I did it for fluid flow. That's a plate we just start moving. But if we think about the heat transfer case, that would be the case where I have a fluid, all one temperature, and then all of a sudden I, introduce a heated plate, right? So maybe I have like a copper plate next to a fluid, so I can heat that copper up really quickly, right? And in a short time it goes to a temperature, and now I start to see temperature diffusing. Or equivalently, I'm trying to do mass diffusion, and all of a sudden I introduce some solute that starts diffusing into the liquid, right? And transiently now that's moving. Okay? So the last thing we need to be able to make this a math problem that we can solve is we need boundary and initial conditions, right? And so that comes from the physical, problem I described. So let's think about what it is. So I have Vx at the y equals 0 point for all time is going to equal V naught. That's what I said is going to happen here, right? As soon as time greater than 0, I start pulling on the plate and it starts moving. Okay. Then I said Vx at infinity at all time is 0. So, super far away, nothing's moving. So that's a boundary condition. And then the last one is Vx at time point 0 at all y is equal to 0, right? So that means I had nothing moving before. And we can write similar things here, right? So I can say t at 0, t is equal to some t naught. T at far away and all time is equal to 0. And t at y, or all y at 0 is equal to 0. And similarly here, I can write CA at 0, t is equal to CA naught. CA at infinity, t is equal to 0, and CA y, 0 is equal to 0. Okay, yes.
When you say that the temperature equals 0 there, is that like ambient temperature? Like
That's a good point. So maybe what we should have said was been a little more careful, and we could have called this, maybe we could call that, yeah, we could call this one T0, we could call this one T1, something like this. And then what we're going to want to do is make this temperature
T minus
subtract and have a reference. Okay, so we could do something like that, and that'll just be a simple change of variable, right, from the absolute temperature to that reference. Or I could define a new temperature scale. We'll call it the Doug scale, and 0 can be the ambient temperature, right, and something like that. Okay. So I'm going to solve the fluid flow problem, but I wanted to point out, because we spent all this time talking about all these others, that this is exactly the same problem for heat transfer, for mass transfer as well, and the same intuition as well.
Dr. Tree,
Yes.
so I can finish wrapping my mind around the analogy ones. In the temperature one, we would not have a flow, right? It would be, the flow would be heat flow, right? We wouldn't.
Yeah, that's right. It's just conduction, right? This could even take place like in a solid. For instance, I could have two solids with conductivity, and one I heat up and put it right next to the other, right? And then that goes like that, right? And the same thing with diffusion. I could be diffusing into a solid, like I could start diffusing into a membrane, for example, and the solid. Yep. Yeah, great question. Yep. Okay. So you're right. Other questions while I'm erasing? Okay, we'll leave that up there for a minute so that we can refer to it if we need. Okay, so now we're going to start 3, method of similarity.
Sorry, like a tree.
Please, yes.
Temperature at y is 0.
Oh, yeah, it needs to be T0. Yeah. Okay, so now we have this PDE, and the question is, how are we going to go about solving? Okay, so we're going to take a little motivation from our dimensional analysis that we did a couple of weeks ago. You were thinking, I thought we just did that on the test or whatever. I'm sick of this, but here it is to stay. Okay, one reason we did it was to be able to have this reasoning. Okay, so let's think about. Let's define. We're gonna use. I want this back. write this up here. Let's do dimensional analysis. Okay, so the book uses a phi as Vx divided by V naught. Okay, so we're going to say, pick that for velocity. And then we have this problem in that, what do we pick as our length scale and our time scale, right? Like we've got X's and T's, or Y's and T's rather, but there's no length scale or time scale in the problem. All I have is a velocity scale, right? Like when I started up the plate, what do? Okay, so we did this problem a little while ago, and so I said, let's just wait for a minute, okay? And let's say I'm gonna have y is gonna be y divided by some length, which I don't know what length, and t, I'm gonna say divided by some time, I don't know what time, okay? And we're gonna plug that back into our problem and see what we get. So making the substitution over there, I'm going to get d v naught v divided by d, let's see, t till tau is equal to a new, I hate doing news, no good at that, new second derivative of v naught v divided by, and then y is y till L squared. Okay, so when I put that together, I'm going to get phi divided by tau d not phi, v naught. Pulling the wrong thing. V naught d phi dt tilde is equal to new v naught divided by L squared, and then the second derivative of phi with respect to our new y squared. Okay? And the v naughts cancel there. And the tau comes over. And so I get d dt tilde is equal to new tau divided by L squared. We'll plug this in here. Okay, so I want to think for a second about the Buckingham pi theorem. You guys remember the Buckingham pi theorem? So in the Buckingham pi theorem, remember, you count the number of independent dimensions and you count the number of variables you have. And that determines how many dimensionless groups you're allowed to have that are independent. Okay, so let's count the number of dimensions. Okay, we have length and mass and time. Right, those are the number. Those are the independent dimensions. Time, length, mass, time. So that means I have three dimensions that I can play with. Okay, and the way you can figure out length, mass, and time, right? You think about the different units I have in the problem, right? I'm certainly going to have length and time, because I've got a velocity and a space and a time, okay? And then I also have this kinematic viscosity, and that viscosity has kilograms in it, viscosity does, okay? So that's what I've got mapped. Okay? So then when I think about the number of variables that I have, okay, and constants and whatnot, and let's see, I have Vx, y, t, I have a v naught, and I have a nu, right? For the kinematic viscosity. Okay, so then I go, okay, how many is that? That's 5 of those. Okay, so how many dimensionless groups should I have? Well, that's just 5 minus 3 equals 2. Okay, so I should have 2. So how many dimensionless groups did I try and have when I made my groups here? Well, let's see, I have phi, that's one of them. I have y hat, that's another one, or y tilde, t tilde, and I have this guy, nu tau over L squared. That's 4. Okay, I'm in trouble. I need to only have 2. Because I'm only allowed to have 2 if this is my number of dimensions and that's my number of variables. All right, so what are we going to do about that? Well, the first one, to get rid of 1, that would be easy enough. If I make this guy equal to 1, right, then I get rid of that group. Okay, but what I'm doing when I'm doing that is I'm essentially saying I can't independently pick the length and the time scale here. Okay, so that gets rid of one of those degrees of freedom. So that's where we came up with, if you remember last time we had this, I said that like the time scale was, equal to L squared over nu, right? And I said, oh, that's the diffusion time scale. Okay, well, they have to be related here because I can't have that extra degree of freedom. Okay, so we'll set that guy equal to 1. I think this was like Roya's question, if you remember when we talked about this. Maybe it makes a little more sense. Think about it with Buckingham pi here. Okay, so that one goes away. So now I'm just left with phi, y, and t. Okay, so I still need to get rid of 1. Okay, so what I'm going to do is I'm going to say, let's define some group that's a combination of y and t. Okay, so that I can, instead of having phi, and I'll have some combination. All right, so I'm going to define y tilde. Do I call it y tilde? No, the book calls it something else. The book says, let's make it a new thing. Let's call this eta. And we're going to call it y divided by g of t, where g is some function of t. Okay, and we don't know what g is. All right, we don't know. We could, there's 2 ways to do this. Okay, one is to make a guess for g based on our dimensional analysis, which is what I'm going to do. The other is we can plug it in and then we can end up solving for g doing an extra math problem. I'm going to do the way where we use our dimensional analysis. If we have time, probably next time when we finish this, you can ask me about the way to do it the other way and I'll sort of sketch it out for you. Okay? But so the way to do this where we make this, we're going to make a guess for g. We're going to use the fact that time and length seem to be related somehow in this way where we have a length squared and a time. So let's assume that if we had, let's see, how do I want to write it? If I had length is equal to nu tau nu root, right? Yeah, move it over. Length is divided by root nu tau, right? If I set that equal to 1, I'm going to say this, right? So what if my g of t had a character that looked like this? What if g of t is something like, or proportional to, here's what I'll say, the square root of nu t, okay? Then it would have the right units that would come out, right? So if I have the square root of time and a square root of nu, that's going to give me the right length units, okay? That seems to make sense. And I'm going to say this is proportional to, so let me throw in a constant there, and I'll say g of t is equal to the square root of some constant that I put in there, just so that I have that constant proportionality. Okay. So I'm going to take this now and plug it into there, and rearrange my equation so that I have things in terms of etas instead of terms of t's and y's. Okay. And if I do this, I'm hoping that this dimensionless group now, instead of having these guys, I'm now have an eta. Okay, yes.
E and gt a tau, or is that just t?
This is a t.
Oh, that's a t?
That's a t.
Oh, okay.
So I'm saying like
Like if we reproduce it.
like this is my intuition.
Yeah.
Right? saying like, we saw that lengths are related to square roots of time. Okay, in our, that's the units are like that. So let me guess that if I put that in there, that will also work out. Yes.
Is the y in eta, is that supposed to be a y tilde?
No, just a y.
Okay,
Okay.
just talking in
So I'm going back and I'm saying, like here I said y was just y divided by some length and t divided by some tau. Let me say, well, what's some length I might use? That length, instead of being, new tau, because I don't have any tau to do, there's no intrinsic time scale. Let me use the time instead. So I'm sort of going back to this stage. And instead of calling it y tilde, I'm going to call it eta, because it's a new variable.
Got it.
That makes sense? Okay, this is the hardest step right here. Okay, this is the hardest thing. The rest is like math from here. So I want to make sure we're kind of like, this is the most unsettling part of it. Okay. Are we all right with this? We're not all right. We're just going to stare blankly and look at the we're transform. We're doing PDEs, and I'm not sure I really want to. Okay. All right. Okay. So let's see. Now we need to make the substitution. So if we kind of retreat back to our original equation, right? So we did this dimensional analysis, but it doesn't really work, right? Because we changed up our variables. What we want to do is instead rewrite this guy in terms of theta and eta, right? So we need to work out what the derivatives are of dvx dt, okay, to be able to find it. So let's write that. If I do dvx dt, and I'm going to note that when I take a partial derivative with respect to t, it's at a constant y. Okay, we'll see why that's useful here in a second. So I need to find, instead, I need to find, I can plug in phi here. So I have v naught phi dt, a constant y. That's just a substitution for the definition of phi. I kept that one. So remember that phi is equal to Vx over V naught. Okay. But I need to do something with this t. I don't have a t anymore. I want to write it in terms of eta, so I'm going to use the chain rule. Right? I want to write this as V naught d phi d eta, and then multiplied by d eta dt. Okay? I'm not allowed to do that, right? And then let's see, I need this guy to be at constant y now, okay? Because that's the time derivative, and if I take the thing with respect to time, I'm not taking it with respect to y, I'm just making that no, okay? So now we can do this, right? We wrote down an eta, so we can go ahead and write this out. So we're going to have a v naught d phi d eta. And now we need to do d eta dt. Let's write d dt of, and then eta is equal to y divided by the square root of c nu t. Okay, and that's a constant y. So now I'm taking the time derivative. I've got a square root of t in the denominator, right? So this is going to be v naught d phi d eta. And then I'm going to have, let's see, if I have 1 over, let's see, that's a t to the minus 1/2. So I'm going to get a minus 1/2 t to the minus 3/2, right? So I'm going to minus 1/2, keep the y. I'm going to have c nu t let's see, that should be to the 3/2, okay? But then I need to multiply by what's inside here, right? So I think I should have another c and a nu on the top. All right? Okay, so if I do that, I have like a v naught d phi eta. And let's see, I've got a y over c nu t to the 1/2. That's another eta, so I can pull an eta out, right? So I can have a minus c nu eta divided by 2. And then I should have a 1 over c nu t in the bottom, right? Because I pulled out a factor of 1/2. Does that make sense? Okay, so then the c nu should cancel. And I should get, let's see, v naught eta over 2t minus sine d eta. Is that right? V naught eta t. Yeah, okay. Got that one. All right, 8 minutes left. See if we can get all the equation written. Do the other one. Okay, we good with this? Okay, so now I need to do the other one. I need to do this dvx dy. That one's going to be a constant t. Okay, well, that's going to be d naught phi dy. This is going to be v naught phi eta dy for this constant t. Okay, so now I need to take the eta dy. Phew, that derivative is easier. Okay, so that's going to give me v naught d eta, and then d eta dy is just going to be 1 over the square root of c. Okay. Then I need to take the second derivative. So the second derivative of vx dy squared is equal to the derivative of the dx dy. Okay, so that's going to be the y derivative of this. But I can take the y derivative and make it this guy, right? So I can have v naught d phi d eta, and then let's see, there's myself. Make sure. All right, let's skip a step. I'm gonna go back. I want to turn that derivative into a, I want to do the chain rule. So I'm going to do phi d eta of dvx dy multiplied by d eta dy, right? That's what I want to do. So I did a chain rule there. Now I have dvx dy, which I did in the last one. So I can plug that in. And I have d eta of v naught d phi d eta 1 over the square root of c near t multiplied by the eta dy. Well, I just did the eta dy, right? For that part right there, that should give me another factor of 1 over the square root of c near t. Okay, so this one is, this derivative here is at constant t, so I should get to pull both of those things out. I should get a v naught divided by c nu t. And then I should have a second derivative of phi with respect to eta squared. Phew, we did it that way. Okay? So now I plug it all together. Back to my, so my original equation, remember, was dvx dt is equal to nu second derivative of x dy. So I got dvx dt nu second derivative of dx dy squared. So let's put that in, and I'm going to have v naught eta divided by 2t dp d eta minus sign, right? Front is equal to a new, and then that piece, v naught c nu t, second derivative of phi with respect to eta squared. Okay, let's see what can cancel. There's a v naught on both sides, so that goes away. There's a nu right here, that can go away. There's a t on both sides, that goes away. And so it looks like I can just move this one over, right, and set it equal to 0. So now I have d squared phi d eta squared plus, I'm going to multiply both sides by c. C is the only thing left in the denominator. So I get c eta over 2 d phi d eta is equal to 0. Phew, okay, we did it. Okay. So what happened? Well, what happened was I converted from the y and t's to this eta, and now I have an ordinary differential equation. I can change these into ordinary differential equation because I don't have any other variables going on, right? This is now an ODE. Okay, second order. Okay, and it's nonlinear, but it's going to be separable, which we'll see. Okay, so we'll be able to integrate it. It's going to work out. So the last thing that we need to do to be able to solve this problem is we need to convert the boundary conditions. With our last minute and a half, let's convert the boundary conditions. Remember, my boundary conditions were out of space over here. I'll just come do it in the class spot. Okay, so remember I had Vx at 0, t was equal to V naught. Okay, so that said that at the bottom, okay, well, that should be pretty easy to convert. Okay, that should be phi, if I divide both sides by V naught, phi at something is equal to 1. Well, what's that something? Let's think about what eta should be. Eta was equal to y over the square root of c nu t. This is at y equals 0, right? So if I have phi as a function of eta only, then that means that should be phi at 0 is equal to 1. So that's one of my boundary conditions. Okay. The other one I had, I said Vx at infinity of t was equal to 0. So that's going to be phi at something is equal to 0, right? If I divide both sides by V naught. Well, where is eta equal to infinity? Or when y is equal, is it?
It's
Y equals infinity. So this should be phi at infinity equals 0. Thanks, Junior. That's my other one. Okay. We might think, well, I had 3 boundary conditions before. Now I only have 2. What do I do with this other boundary condition? So the other boundary condition was Vx at all y comma 0 equals 0. Well, look at that. If I put in t equals 0 into this, I end up with that exact same boundary condition. That makes me feel a little better. Okay, so my boundary conditions also collapsed into just one boundary condition. Okay, those 2. So now I have an ODE, second order, 2 boundary conditions, just like I would expect. Okay, and we can solve it next time. Okay, that's all I got. Yeah.
In the far right equation, second line down, what is the second term in the first denominator term? Next to it, that's that two. On the other side of the equation.
Two?
Oh, is that a two? I thought, okay, I thought that was a new.
I don't know where you fit.